Hi, I'm Ilse from Daisy, Germany, and I'll be talking about RNO, the Radio Neutrino Observatory in Greenland. And we're using the radio technique, so the radio emission that's coming from the particle shower when a neutrino interacts in the ice to detect neutrinos. We have not seen such a neutrino with this technique, no one, simply because it's quite new. So all the experiments that are there are not large enough to actually detect something. So yeah, why do we need a new technique to detect neutrinos? Because, I mean, we have, for example, IceCube, which is very, very big. So all the other experiments that are there until now are not sensitive for the they have not detected neutrinos at the very high energies, simply because they are too small. And what is so nice about radio is that the attenuation length is very long, so it's a few 100 kilometers up to a kilometer. So radio propagates very far, and therefore you can instrument your volume with a low density of detectors to cover very large volumes. So for these high energies, you can see here the sensitivity for RNO, and for these high energies, Earth absorption comes in, and therefore we're sensitive to the northern sky, since we're located in Greenland. Here you can see the planned layout. So currently we have funding for 35 stations, and we started deploying last year. So we're located really in the middle of Greenland at Summit Station, facilitated by NSF at a 3-kilometer ice sheet. And the 35 stations have a spacing of 1.25 kilometers, which is to maximize our effective volume, such that most neutrinos will only be seen by a single station. So we spread them out as far as possible. Some, however, will be seen by multiple stations. And therefore, our stations are also optimized to do neutrino reconstruction with a single station. It looks like a big effort, 35 stations, 1.2 kilometers. That is also the case. However, their stations are quite easily deployable, like 4 days per station, and they have their own power, and therefore it's a very doable effort. So this is one single RNO station. And as you can see, it has 3 strings of 100 meters each, and it has some antennas near the surface. They're also in the ice, so all the antennas are in the ice, but just very near the surface. And Lily, she's right there, she will talk about it tomorrow, about what we do with the surface component. So the 3 strings are for azimuthal reconstruction of the neutrino, and then there's this one string that has a lot of antennas near the bottom, which we used to coherently add all the waveforms, such that you can lower your noise, and then you can trigger very low threshold. And then it has more antennas, more up, and you can use all the timing differences of the waveforms to actually do some distance reconstruction from where your neutrino interacted. So when you to deploy these strings, you need deep holes, of course. So they're 30 centimeters wide, and they are deployed by the British Antarctic Survey, which is a company that comes with us every year to Greenland to actually make our holes. And it's a mechanical drill, so it's like ice coring. So you go in, collect the ice, go out, and then you throw out the ice. And when you have the holes, you can put in here on ropes your antennas, and you drop them all the way down. So we deployed the first stations last year, 3 last year, and the last few weeks, actually, we have 4 more stations that were deployed. So last year was very exciting because we had our first data. So we could check how our system was working. And what you can already see here, so here you see a station that was deployed last year, which is the trigger rate versus the time. And you can see like this green blobs during the day of 8 hours, which is really self-induced noise. So we were causing a lot of our own triggered events, but it was a very efficient iteration last year already that we got rid of them. We see, of course, a bunch of other events like radio snowmobiles. And another interesting thing that we saw is that for when there are high winds, then we see way more events, which is also seen by other radio detectors in polar areas. So it's a paper published that you can see here. Because radio is propagating so far in the ice before we actually see them, it's important to know what is the ice doing to the radio propagation, to the radio. And therefore you need the attenuation length. So last year we took a bunch of data to determine what the attenuation length of our ice in Greenland is, which we also published. And then each station has two pulsars deep in the ice and one near the surface to calibrate our system and to mainly to determine where our antennas are located and to monitor snow accumulation. So that was the more general part of RNO. Let me focus a bit more on direction reconstruction, where the neutrinos come from, because it's not super straightforward. When we have our neutrino coming in and it interacts in the ice, then the particle shower is generating radio emission. But because the ice is very dense, the Cherenkov angle is 56 degrees, and therefore the radio emission is on this cone of 56 degrees. Meaning that if you detect your radio emission here at your detector, it could still come from anywhere on this cone. So you don't really know. So when you detect your radio emission here, and it could come anywhere from this cone, but this could also be the cone. So you don't really know where your neutrino comes from. Luckily, due to the radio mechanism, we know how the electric field is polarized. And therefore, if you can also determine the polarization, you know where your neutrino pinpoints to. But to know the polarization, you need to have perpendicular components of the electric field. So you need antennas detecting different components. And you can imagine that if you're very deep with very narrow 30-centimeter holes, that it's very easy to make antennas that detect the vertical component, but way harder to detect the horizontal component. And therefore, that is also the limiting factor in determining the direction where the neutrinos come from. Because our H-poles, so we call them H-poles and V-poles, the H-poles are way less sensitive. So let me go one slide back. So the opening angle between the radio emission and your neutrino direction, that's what we call the viewing angle. So what you need is you need your signal direction, your viewing angle, and the polarization to actually know where your neutrino comes from. So if you have your viewing angle, you can point it back to this whole cone on the sky, and you need your polarization to actually limit it down. So what is the dependence of the incoming zenith direction of the neutrino? So for very vertical showers, as you can see here, because we have a cone of 56 degrees, due to the geometry, we cannot see them with our antennas. So we're not sensitive to vertical showers. If you go more horizontal, we are sensitive. And the difference by going even more horizontal is that you can, purely due to the geometry, see a way larger part of the cone that is actually possible to reach your detector. Yeah, this is important, comes in later. So if we want to quote what our angular resolution is, what is then important? So let me give you 2 slides with things you already know. So dependent on if you actually have a neutrino or not, or what your question is, you want to know what is your point spread function. So how do you observe a flux of neutrinos coming from a source with your imperfect detector? Or if you have a neutrino, you want to know where could all this neutrino come from? So what is your single event uncertainty? And then you correlate it with your source. So what you have for each of your events, you have for each direction, how likely is it that this neutrino can come from this direction? And if you think that you know your detector very well, you can use the difference in angle between where the neutrino comes from and you reconstruct it, and you can histogram them, and then you have your space angle, which is really a representation of the least information that you can get from all these landscapes. If you really include everything, so you add all these, then you have your point spread function. So then you know what you expect from a specific direction. And if everything is easy, and this is nicely 1D, then you can actually describe it with your space angle. However, due to the geometry, we expect for different zenith directions that more polarization options are possible. And therefore, depending on the zenith direction, we have this directions basically that are not possible. And therefore, this figure really depends on your zenith direction and is especially not 1D. If you want to include more information, then actually reduce this entire landscape to a single number. You can include the shape. For example, by drawing contours such that all your values are lower than your simulated one. And in the ideal world, when everything is 1D, you can again describe it with your space angle, which for us is not the case, because limiting to this band on the sky, we end up with this very narrow band ellipse shape contours. And this is very asymmetric, so it can have ratios of 1:10, how this ellipse looks like. So what do we do to actually give uncertainties to our events? So we reconstruct here a single event a bunch of times with the systematics, which is mainly determined by the thermal noise of the antennas itself. And you can see that it's indeed ellipse-like. And if you then go to the coordinate system of polarization and viewing angle, then you can see that it's nicely uncorrelated. So we can describe the long axis with the polarization and the small axis with the viewing angle, as we would also expect. So we parameterize this for all the events that we have, mainly dependent on the amplitude in our v-poles and the amplitude in our h-poles. So to give you an impression of what would it look like for RNO. So what is now our angular resolution? If we look at all the events, we have at the 90% contour, we have 35 squared degrees, but we can limit it a lot if we have actually h-pole contribution to 10 squared degrees. And if we look at the space angle, we can do median of 3 and 1.3 degrees, depending on we have h-pole or not. And the h-poles still contain almost a fifth of the events. Then I have my summary slide. So RNO is going to be the first experiment, most likely, that will be sensitive to neutrinos for these very high energies with the expected fluxes. So far we deployed 7 stations. And I all want to point you to Lily's talk tomorrow. And I think I leave it